Okay, Chapter 9, Section 3 is titled Geometric Sequence and Series. So key here is that we're talking about a new type of sequence, different than the arithmetic sequence we talked about yesterday, and we're going to call it a geometric sequence. Okay, so let's go ahead and start with the definition of a geometric sequence. Geometric sequence is a sequence in which the ratio between consecutive terms is constant. So think about what a ratio is. A ratio is a relationship between two quantities. A lot of times we can represent ratios as fractions. So basically, when you're working with a geometric sequence, in order to get to the next number, instead of adding or subtracting the same thing every time like we did yesterday, now we're either multiplying or dividing by the same thing every time. So this idea of the ratio between consecutive terms being constant would tell us if we take the second term, divide it by the first term, because those are consecutive terms, that should be equal to the third term divided by the second term, which should be equal to the fourth term divided by the third term, fifth term divided by the fourth term, so on and so on, such that that is equal to R, where we would call R, similar to yesterday, we called D our common difference. Now we're calling this our common ratio. Okay. There is one special thing that we'll say here, such that R is not equal to 0. You could imagine if your ratio was 0, that would not make for a very exciting sequence full of zeros. So here we would specify R cannot equal 0. Now, if you're always dividing by the same number to get to the next term, so like if your numbers are becoming smaller because you're dividing, note that your ratio will be a fraction. So if you're not multiplying by 5, but rather dividing by 5, then your ratio will be 1/5. So that's something to keep in mind as you work. The formula for geometric sequence is actually a pretty simple formula. It just says a sub n is equal to a sub 1. So of course this is talking about our first term, times R, which is our common ratio that we just talked about, raised to the n minus 1, where n is the number term that you want. So if you want the 10th term, you're going to raise it to the 10 minus 1, or 9. I'm always careful to put my R in parentheses in the case of my ratio being negative. And we can also think about that very first day, Monday, when we talked in class, if you had like -1 raised to certain exponents, -1 to the n or -1 to the n plus 1, anytime your ratio would be a negative, then that's going to introduce alternating signs for your sequence. Oops. So let's put that to use in an example where we're being asked to write the expression for the nth term of a sequence and then find the indicated term. So we're being asked to do two things. The first thing I'm going to do is write the expression for the nth term. So I'm going to model that after the formula that we just saw. A sub n equals a sub 1 times R to the n minus 1. Well, do I know my first term and my ratio? Yes, just plug them in. A sub n equals 1 times the square root of 3 raised to the n minus 1. And certainly you could write that as just the square root of 3 times, or raised to the n minus 1. You don't really need the 1 in the front. Okay. Now, it's also asking me to find the indicated term, which is n equals 8. So I want to find the 8th term. A sub 8 is equal to 1 times the square root of 3 raised to the 8 minus 1. That is a square root of 3 raised to the 7th power. For most of us, if we plug that into the calculator, it would give us a decimal answer. To avoid a decimal answer, I'm just going to think about what I know about a square root of 3. If I multiply a square root of 3 times another square root of 3, I'm going to get 3. So I'm going to think about, if I were to write out 7 square roots of 3, how many pairs would I have? I'd have actually 3 pairs of the square root of 3, so that's going to be 3 times 3 times 3. That's the square root of 3 times the square root of 3. Is 3, and we can do that 3 different times. That'll use up 6 of our square roots of 3. And then to get to 7, of course, I have 1 more square root of 3. And so to avoid fractions, not fractions, decimals for my 8th term, I can simply write this as 3 times 3 times 3, which is 27, times the square root of 3. Okay. If you want to verify that that's correct, you could go ahead and plug that into your calculator, 27 square root of 3, and then also do square root of 3 raised to the 7th. They should be the same answer, so you would know you were correct. We'll look at one other example with writing the nth term, and this is similar to one that we did yesterday, where instead of giving you the first term, I give you two different terms in the geometric sequence. Now, there are multiple ways to answer this question, so there's more than one way to find your first term and your common difference. I'm going to show you an algebraic method to solve for that first term and the not common difference, but common ratio. Okay. So when I see that I have a second term equal to 3, I think about that, how we talked about on Monday, the very first day in class. That's an ordered pair, 2, 3, on the graph of my sequence, where 2 is my n value. It's the number term that I'm talking about, and 3 is the actual term, a sub n. I also have another ordered pair, 5 and 3 over 64. So what I can do with those terms, because they represent n and a sub n, I can substitute them into the formula that we just worked with. So I would say something here like 3 equals a sub 1, which I don't know, times the ratio, which I don't know, raised to the n minus 1, which I know is 2 minus 1. So then I come up with 3 equals a sub 1 times r. Okay. Now, that doesn't really help me out, but what I can do is solve for one of those variables. I will say that I generally solve for a sub 1, so I try to get a sub 1 all by itself, because in some cases r might have another exponent besides 1. So I'm going to divide both sides by r, so I know my very first term, a sub 1, is equal to 3 divided by r. Okay. Now, again, not very helpful, but what I could do with that is take my second point, a sub 5 equals 3 over 64, plug 3 over 64 in for a sub n. My a sub 1 that I just found, 3 divided by r, I can plug in for my a sub 1. And then that's going to be multiplied by r raised to the n minus 1, which would be 5 minus 1. So that's 3 over 64 equals 3 over r times r to the 4th. And be careful not to get cancel happy and cancel out your r's. You have to account for that exponent. R to the 4th divided by r is, of course, r cubed. So I have 3 over 64 equals 3r cubed. And now my goal would be just solve for my ratio. So divide both sides by 3. Oh, and maybe because the other side is a fraction, rather than dividing by 3, I'm going to multiply by 1/3. That will work out a little bit nicer in my work. The 3's cancel, actually on both sides. And so I have 1 over 64 equals r cubed. To get r all by itself, then I would have to cube root both sides. When you cube root 1 over 64, the cube root of 1 is 1. The cube root of 64 is 4. So my ratio is 1/4. If I know my ratio is 1/4, then I can plug that into my a sub 1 expression to solve for a sub 1. So 3 divided by 1/4. Remember, you'd really be multiplying by the reciprocal, so that's really 3 times 4 over 1, which tells me that a sub 1 is 12. Okay. So now I can take that a sub 1, 12, the r is 1/4, and plug them in to my a sub n equals 12 times 1/4 raised to the n minus 1. So I have written the expression for the term, the nth term in the sequence. It does ask me, just like our last question, to find the indicated term. So I'd be trying to find the 7th term. I could do something like a to the n equals 12 times 1/4 raised to the 7 minus 1, which is a sub n equals 12 times 1/4 to the 6th. If you want to avoid decimals, I could change the a sub n's to a sub 7's because I'm finding the 7th term. If you want to avoid decimals, then just figure out what 4 to the 6th is. And 4 to the 6th is 4,096, and you could reduce that fraction. I get 3 over 120 or 1,024, and then you could also write that as a decimal. If you chose to. It's like 0.0029 3. Okay, maybe if you wrote it out as a decimal. I try to avoid the decimals if I can, but sometimes it's not really possible. Okay, so that's one way to solve for that equation and the indicated term. Now, notice I had said at the beginning, that's not the only way to do it, but it is one way, okay, and it's a way that will always work. I like it because if you can remember back to chapter 3, it's a lot like how we wrote our models for exponential growth and decay. Okay, moving right along, so we've kind of talked about sequences. Now we kind of get on that piece where we're going to talk about series, and we're going to talk about 2 types of geometric series. So this is the formula for the finite geometric series. For finite geometric series, we're going to do S sub n equals a sub 1 times 1 minus r to the n divided by 1 minus r. When you see this formula in a textbook, it's going to have that large group of parentheses there. But one thing I always note to my calculator users, especially if you don't have math print with the fractions, if you're going to type this all into a calculator at once, you're going to need to put the 1 minus r to the n in the numerator in parentheses, and also the 1 minus r in the denominator in parentheses, so that you get the correct answer. Remember, S sub n represents the sum of the series, okay, as opposed to finding a term. Okay, so we want to find the sum of the the finite geometric sequence, or that should say series, finite geometric series. And we have summation notation. So you need to kind of pick apart the summation notation. So if you're thinking about that formula on our previous slide, can you find the first term? You'll need the ratio and the number of terms that you want to add up. So you're going to need a sub 1, r, and n. Okay. Well, in the formula, it's pretty easy. A sub 1 is 16, r is my negative 1/2. In summation notation, to find your value for n, you'd be looking at your upper limit. So I'm adding from the first term to the 12th term, so I really want to add up 12 terms. So that's going to be my n value. I'm going to go ahead and plug that into the formula. The sum of the first 12 terms in this geometric series is equal to 16 times 1 minus, and I'm going to use a parentheses for my negative 1/2, raised to the 12th, and then divide by 1 minus negative 1/2. And then my larger group of parentheses. Be really careful with this numerator in the 1 minus negative 1/2 to the 12th. You're going to have to take the ratio raised to the exponent first, which in this case is going to make it a positive number, and then 1 minus that number is going to be a positive value. Okay, you're going to be doing 1 minus that positive number. Whereas if you distribute or you do negative and make that plus a positive, then you'd be adding 1 plus 2 to the or 1 plus 1 over 2 to the 12th. So be really careful with that when you're using that work. You know, if I think about 2 to the 12th, I know that that's going to be a very large number. So this is a problem where I would probably just go ahead and plug it into my calculator. Remember, when I plug it into my calculator, I'm actually going to add some extra parentheses there, so that I'm putting parentheses around the numerator, and then I've got those parentheses for my negative 1/2. And then I'm going to put parentheses around my denominator and more parentheses for my negative 1/2. And I come up with a total of 10.664. There are some extra numbers, but I'll just go to the thousands there. You could certainly use your fraction button. That is 1,365 divided by 128 if you don't want to round. So this is an example where, because your number is really, really small, maybe a decimal answer would be appropriate. Okay, now we have one other example where instead of finding the actual sum, we want to just use the summation notation to write the sum. So I want to put it back into that sigma notation. Think about the things that you would need for sigma notation. I'll start with my lower limit. I'm going to go ahead and call 15 a sub 1. So I'll use an index of I and say that I is equal to 1. Okay. I'd like to find out what my upper limit is. So I'm going to need that upper limit. I've got to find out how many terms are being added here. If you want, you can think about it more like a sequence. 15, -3, positive 3/5, and then dot, 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 -3/625. Okay, that's going to be my ending term. So I really have to figure out like what term is that -3/625. So I'm going to start first actually by using my common ratio. So if I were to do -3 divided by 15, I would come up with -1/5. And that should be the same if I were to do 3/5 divided by -3. And it is also -1/5. So I know my ratio is -1/5. I've got to think about like how many terms out is this -3/625. Now, there are several ways to do this. I would guess some of you might look at that and say, like, I could just figure out how many more times, based on the fact that this is 3/5, how many more times would I have to multiply by -1/5 to get to that -3/625. So if I multiply, if I get a fourth term, it would have a denominator of 25. If I did a fifth term, it would have a denominator of 125. And then if I multiplied by -1/5 again, then my denominator would finally be -625. So that was fourth term was 25 denominator, fifth term was 125. So I'm thinking in my head that this is the sixth term, so that should be my upper limit. Okay. Now, if that's too far out and you want to figure out what term that actually is, you could do -3/625 as your a sub n. You could write the rule, so we know our first term is 15, our ratio is -1/5, and we want to raise it to the n-1. Okay. To solve for this n in the exponent, I'm going to have to get the exponent and its base all by itself, so multiply by 1/15. Okay. In this case, to avoid a decimal in my calculator, I'm just going to do 15 times 625, which is -3/9,375. That's equal to -1/5 raised to the n-1. Okay. And then the next thing I could do is write this as, let's see if this is going to work. No answer. Normally I would say write it as a log, but we're going to have an issue because our base is a -1/5. Our ratio. So I would say on this one, just so I can show you the log process, like that -1/5 is just the thing that's alternating the signs. So I'm actually at this point, I'm just going to worry more about 3/9,375 is equal to 1/5 to the n-1. So you can't really divide by -1 there, but I know that negative, if you think back to Monday, it's just the thing that's alternating my sign. So now I'm going to start at my base, which is 1/5. I'm going to say the log base 1/5 of, and then I got to go around the equal sign. So 3 divided by 9,375 should be equal to n-1. And then if you'll remember, back to chapter 3, I can evaluate this log. The log of 3 divided by 9,375 all over the log of 1/5. That's my change of base. Some of you have that special button or capability in your calculator to type in a different base. And so I get 0.2. Oh no, I typed it in incorrectly. That makes sense. So the log of 3 divided by 9,375 divided by the log of 1 divided by 5. We get 5. Okay, good. So then I know that 5 is equal to n minus 1. So I'm kind of going all over here, but I'll take this back up here. That log evaluates to be 5. 5 is equal to n minus 1. Add 1 to both sides, and sure enough, n is equal to 6. Now, I'm sure most of you are looking at all that work with the logs and thinking, I would just rather figure out how many times I multiplied. I think, honestly, in this particular problem, that's probably the most efficient way for you to do that. Just know that if you ever did get really stuck and you couldn't figure out what term it is, that you do have knowledge about logarithms, and that's how you would be able to solve for the exponent in the geometric series. So I'm going to finish this out. I've got that upper limit, which that algebra verified what I thought was going to happen, so my upper limit is 6. And then I just need to get that rule behind it, which I already used the rule so that I could solve. It's a sub 1, which is 15, times my ratio negative 1/5, and then raised to the, should be I minus 1 because I used an index of I. If you want to use index of n in your summation notation, you could do that. Okay, so this piece right here is my summation notation to write that sum of the series. Okay. Again, if you like this stuff, the thought process we used early on to figure out the upper limit, you can go ahead and use that. Just know that logs are a backup if you need them. Okay, so we have one other thing to talk about, and that's the sum or the formula for the infinite geometric series. Nice thing about this formula, I think you can tell just by looking at it, it's a little bit more simple formula. So we just have the sum, and we don't have a s sub n anymore because we're not adding up a certain number of terms. The sum is equal to a sub 1 divided by 1 minus r. Again, if you're typing that into a calculator, you would want to have parentheses around your 1 minus r. So you really only need a sub 1, your first term, and r in order to be able to calculate the sum of an infinite geometric series. Okay. So we want to find the sum of the infinite geometric series. Okay. I'm thinking about that formula. S equals a sub 1 divided by 1 minus r. And so I really need to know what is my first term. 5, so I've got that. I want to do 1 minus my ratio, so now I'm going to do my second term divided by my first term, 1/5. If I want to verify, I could do my third term divided by my first term, which 0.2 is 1/5, so on and so on. So that's going to be my common ratio. And so I really have 5 divided by 1 minus 1/5 is 4/5. And again, if you're dividing by a fraction, you're really multiplying by its reciprocal. So 5 times 5 over 4, that's 25 over 4. And that should be 6.25 if you write that out as a decimal. Okay, but I'll generally just leave it as a fraction. Okay, so again, that one's pretty simple. Just need the first term and the ratio. There's one example that I want to look at. Find the rational number representation of the repeating decimal. And this is a really interesting problem, so that if you have a repeating decimal, how can you ever write it as a fraction? Well, you can use series or infinite geometric series. So how do we use the infinite geometric series to write this repeating decimal as a rational number or as a fraction? Here's the thing you have to remember. You have to start, or you have to think really carefully about, like, you really want to focus on the series part of it as the part that is repeating. So notice that there is a part of this decimal that is not repeating. That is my 0.5. So I'm really going to kind of keep that separate. And I'm going to think about it as 0.5 plus 0.09 plus 0.00. I'm thinking about this. Keep going, right? 0.0009 plus 0.000009. Okay, and what I'm going to do there is I can write this as, powers of 10. So this is really 5 over 10 because it's in the 10th spot of the decimal. The 9 is the first 9 is in the 100th spot, so that's really 9 over 10 squared. Now there is a 0. If you want to write that, you could say plus 0 over 10 cubed if you don't want to skip over the 10 cubed. But I didn't actually write that in my sum there. So I'm going to cross that off because I don't really have that represented. But then it will be 9 over 10 to the 4th, because there's a 0 in the thousandths, there's another 9 in the 10,000ths. Okay, so that would be 10 to the 4th. And then there is a plus 0 over 10 to the 5th. But again, I don't have that represented. Plus 9 over 10 to the 6th. And at this point, I think you can kind of pick up on the pattern. So again, I said you can kind of ignore for a little bit that 0.5 or that 5 over 10. You're going to focus on this 9 over 10 squared plus 9 over 10 to the 4th plus 9 over 10 to the 6th, so on and so on. And we just keep adding because this decimal is just repeating, okay? And so I'm going to think about this like a geometric series, okay? And it's infinite, so it's going on forever. So I can identify the first term. The first term is a sub 1. The other thing I would want to be able to do is figure out my ratio. My ratio is 9 divided by 10 to the 4th. And then I would divide by the first term, 9 over 10 squared, which is really multiplying by its reciprocal, 10 squared over 9. And you can see very nicely here, the 9's will cancel, 10 squared over 10 to the 4th. My common ratio is 1 over 10 squared. And you can also see that like, what are you doing to get to the next term, 9 over 10 to the 4th? You're just multiplying by 1 over 10 squared. Okay, so what I did right there was I identified my first term, I identified my ratio, and this series goes on forever because it's a repeating decimal. So what I want to do with this whole chunk right here, all the way from 9 over 10 squared, and this just keeps going, okay, is I want to calculate the sum of the infinite series. So the sum is the first term, 9 over 10 squared, divided by 1 minus 1 over 10 squared. Okay, so a sub 1 divided by 1 minus r. And then I can change this into fractions, or actual numbers. 9 over 100 divided by, this would be 1 minus 1 over 100. So if you take away 1/100th, you have 99/100ths left. When you divide by a fraction, 99 over 100, you're actually multiplying by 100 over 99. Your 100s will cancel, and 9 over 99 is 1 over 11. So the sum of that particular infinite geometric series would be 1 over 11. And remember, that's not the whole problem, because I had previously said you don't really have to worry about this 5 over 10. So now I'm going to bring that 5/10 down here. It's really 5/10 plus whatever that sum was, 1 over 11. And now I have two fractions that I need to add. In order to be able to add them, I need common denominators. And so that gets me something like 55 over 110 plus 10 over 110, which is 65 over 110. And those are both divisible by 5, so that gets me 13 over 22. That is a reduced fraction, and if you type 13 divided by 22 into your calculators, you're going to see you get that repeating decimal, 5.90909090. So it is a lot of work. It's an interesting thing to think about, because the idea that if the decimal is repeating, you should be able to write it as a fraction, because that's a rational number. So this is one way that we can do it. Okay, I know you've done a couple of really long problems, and they're good problems to think about. If you're working on your homework, certainly some of them are going to be easy and quick, and then some of them are going to take more time. Don't try to put all of your work into too small of a space. That leads to much frustration. and work carefully. Remember, for all the odds, please check those in the back of the book, and we'll go over questions tomorrow, do some group problems, and you have a quiz on Friday.